In this lesson, we're going to wrap up our exploration of stereochemistry, taking a look at optical activity and the stereochemical relationships of enantiomers and diastereomers. Optical activity is the rotation of plane polarized light by a chiral compound. And only chiral compounds can do this. Achiral molecules like water do not have this optical activity. And if you don't know what plane polarized light is, just imagine light traveling through space. As it travels, it has an infinite number of vibrational planes. Plane polarized light simply filters all that out so that all the vibrations are in parallel planes. Now, if the chiral compound rotates this plane polarized light clockwise or to the right, it's called dextrorotatory and it's notated with a plus sign. If the chiral compound rotates this plane polarized light counterclockwise or to the left, it's called levorotatory and it's notated with a negative. The optical activity for a compound can be measured using a polarimeter. A basic polarimeter is nothing more than a tube that holds a solution of the chiral compound being analyzed. Plane polarized light is passed through this tube, and as the light passes through the sample, the chiral molecules inside rotate the plane of vibration of that light, which can then be measured with a polarizer at the opposite end. That angle of rotation is called the observed rotation, and it's abbreviated with an alpha. Now, in and of itself, this observed rotation is not that useful. If you think about it, the extent of rotation is going to be dependent on how many molecules the light passed through, and that is a factor of the concentration of the sample and the length of the tube. If we divide the observed rotation by the length of the tube and the concentration, we get a specific rotation. And the specific rotation will actually be a constant for any given chiral molecule. Each chiral molecule has its own specific rotation. We'll see the importance of optical activity later on in this lesson. Now, all stereoisomers are related either as enantiomers or diastereomers. We're going to look at enantiomers first. Enantiomers are a pair of non-identical mirror images. And that statement may sound kind of familiar. We actually define chirality as a property in which an object has a non-identical mirror image. Well, when a compound or object has a non-identical mirror image, those two objects, the object and its mirror image, are enantiomers. So here, I have a pair of 3D models, and you can see that these are non-superimposable mirror images. They're enantiomers. For molecules that have only one chiral center, one enantiomer will be the R configuration, and the other will be the S configuration. Now, a pair of enantiomers have an awful lot in common. In fact, they have most things in common. Things like your general physical properties and a lot of chemical behavior. So things like boiling point, melting point, densities, color, all those things are going to be the same, whether you're looking at the R enantiomer or the S enantiomer. But enantiomers are different in two very important ways. Each enantiomer interacts with other chiral molecules uniquely, and each enantiomer will have the same but opposite specific rotation. If one of them is dextrorotatory, the other will be levorotatory, but to the exact same angle. So here I have an example of an alcohol, and it's a chiral molecule. We can see that one enantiomer is the S and one enantiomer is the R, and the specific rotations are the same value but in opposite directions. The S enantiomer happens to be plus 13.5 degrees, and the R enantiomer happens to be minus 13.5 degrees. And do keep in mind that there is no correlation between whether a molecule is dextrorotatory or levorotatory and whether it is R or S. Some molecules that are R are dextrorotatory, and some molecules that are R are levorotatory. There's no connection there. But you can see now some of the importance of optical activity. If you have two compounds that are enantiomers, and if all of their general physical properties are the same, then how can you tell which enantiomer you might have? Well, one of the few ways we can actually tell one enantiomer from another is by taking a specific rotation measurement using a polarimeter. When chiral compounds are made, either by nature or synthetically, they are often made as mixtures of enantiomers. And this brings about a new issue with respect to purity. Think about it. If you say that something is 100% pure, you have a bottle of water and you say it's 100% pure water. That means that every molecule in there is water. Now you can say the same thing about a chiral compound. Carvone is a chiral compound found in nature. One enantiomer comes from spearmint and the other one comes from caraway. The two enantiomers have different scents associated with them. Now let's say you were manufacturing some chewing gum and you wanted to put carvone in that gum as a flavoring agent. Well, when you order that carvone from the supplier, you're going to want to know whether it's 100% one enantiomer or the other, or if it's a mixture. If you're trying to make spearmint gum, you want to make sure that it's all the spearmint flavored enantiomer. So not only do you want it to be 100% carvone, you want it to be 100% a specific enantiomer of carvone. The idea of optical purity is a measurement of how much of one enantiomer is present versus another in a mixture. Optical purity is recorded as something called an enantiomeric excess, and it's reported as a percentage. But that percentage doesn't mean what you probably think it means. Let's take a look at how it's calculated. Enantiomeric excess is calculated by determining the specific rotation of a mixture that you're analyzing and then dividing that by the specific rotation of a pure enantiomer and then multiplying that times 100%. So let's demonstrate this with a couple of simple cases. It turns out that the enantiomer of carvone that has that spearmint flavor is the R enantiomer, and it has a specific rotation of negative 61 degrees. So if you had a pure sample of the R enantiomer, then when you measured its specific rotation using a polarimeter, you would get negative 61 degrees. Then divide by the actual specific rotation, which is negative 61 degrees, and you get 1 times 100 is 100%. But think about what would happen if you had a 50-50 mixture of the R and the S enantiomers. As much as the R enantiomer would rotate the light one direction, the S enantiomer would rotate it the exact same amount in the opposite direction. In other words, the two rotations would cancel each other out, and you would wind up with a rotation of 0 degrees. So you place 0 degrees into the numerator, divide by the actual specific rotation of the R enantiomer, which is negative 61 degrees, and you get 0 times 100%, and that means that the EE would be 0%. The EE is 0% even though it's a 50-50 mixture of the two enantiomers. And that's what I mean by this value doesn't mean what you think it means. It literally means an excess of one enantiomer over the other. And think about it, in a 50-50 mixture, how much excess of one enantiomer is there versus the other? None. There is a 0% excess of one over the other. So a 0% EE actually means you have a 50% R, 50% S mixture. And as I've kind of hinted at, optical purity is really important in certain industries, particularly the food and drug industries. A chiral fragrance molecule or flavoring molecule can have very different scents or flavors associated with it depending on which enantiomer you have. And the same thing is true for drug molecules. Chiral drug molecules can have very different effects or at least different efficacies based on which enantiomer of the drug molecule you have. So this idea of optical purity, which is calculated through optical activity, is really, really important. Lastly, that 50-50 mixture of enantiomers I mentioned before has a name. It's called a racemic mixture or racemate. And of course, a racemic mixture is going to have a specific rotation of 0 degrees and an EE of 0%, right? Because there's no excess of one versus the other. Now, the other stereochemical relationship that molecules can have is to be diastereomers. And diastereomers are kind of a catch-all. Diastereomers are simply stereoisomers that are not enantiomers. In other words, they're not mirror images, but they are still stereoisomers. So here I've got a couple of 3D models that demonstrate this. If you look, you can see that these are in fact stereoisomers. The left carbon of each molecule has the same 3 groups attached to it, a green, a purple, and a white, and the right carbon has the same 3 groups attached to it, in each case, green, orange, and white. But the spatial arrangements are different, and they're not interconvertible by simple free rotation, so they're not just different conformations of the same molecule. Diastereomerism is often found in compounds where you actually have multiple chiral centers, and that's what we see in these molecules here, right? Each compound has 2 chiral centers. Now, just because a molecule has more than one chiral center doesn't mean that all of its stereoisomers are diastereomers. Let's take a look at this example over here. We can see we have 4 stereoisomers drawn out as Fisher projections, and I've gone ahead and annotated these with the configurations of all the chiral centers. If you look at this first one on the top left, you can see that the top carbon has a configuration of R and the bottom carbon has a configuration of S. The compound just to the right of it has a configuration of S for the top carbon and R for the bottom carbon. And if you think about it, that means that these have to be enantiomers. The way I have them drawn out here makes it rather easy to see. You can imagine a mirror in between those two molecules reflecting each so that they are in fact mirror images. And again, they're not the same, but they're mirror images, therefore they are enantiomers. The same is true for the bottom pair of molecules. The one on the left, the top configuration for that carbon is S, and on the bottom is also S. And the molecule on the right, the top carbon, that configuration is R, and the bottom carbon is R. Again, you can see they literally look like mirror images of one another, right, in terms of how the different groups are distributed in space. But you'll always know you have the mirror image of something when you have swapped all of the configurations. If you look at the top pair, those enantiomers had configurations of RS and then SR. We reversed or inverted all of them. And the same thing is true for the bottom pair. On the left, we had SS, and if you invert that, you get RR, and that's the enantiomer. Now, the relationship between any two other stereoisomers here is going to be diastereomers. If you look at the left pair, you can see that the top one of that left pair has configurations of R and S, and the lower one has configurations of S and S. They don't look like mirror images, and they're not mirror images. The configurations on the bottom carbons are the same, right? They're both S. They even look the same. But the configurations on the top carbons for those left molecules are opposite one another. So if you ever invert some, but not all, of the chiral centers on a molecule, you will have created a diastereomer. If you look at the right pair of molecules, you'll see the same idea. The top molecule has configurations of S and R, and the bottom one has configurations of R and R. So we swapped out, we inverted the top one, but we left the bottom one alone. And when you invert some, but not all, you wind up with diastereomers. And then you'll see the same thing going diagonally, right? The top left and bottom right are diastereomers of one another, and the top right and bottom left are diastereomers of one another. Now you might remember that enantiomers had all the same general physical and chemical properties, things like boiling points and melting points, etc. With diastereomers, that's not true. A set of diastereomers will often have similar, but not necessarily the same properties. So things like boiling point, melting point might be similar from one diastereomer to another, but not necessarily the same. Now, just like we saw with enantiomers, the different diastereomers will interact with other chiral molecules differently. The different diastereomers will also have different specific rotations. However, unlike with enantiomers, there is no relationship. Remember, with a pair of enantiomers, the specific rotations were the same in intensity but opposite in direction. With diastereomers, there's just absolutely no relationship from one diastereomer to the other with respect to the specific rotation. We've got one last little thing to look at, and that is the idea of a meso compound. A meso compound is a molecule that has chiral centers, but is in fact not chiral. So it's achiral. The reason that a meso compound can have chiral centers but not be chiral overall is because the chiral centers are symmetrically distributed across the molecule. So here I've got a 3D model to demonstrate it. And you can see in those two carbons, those are two chiral centers. They each have 4 different groups attached to them. The one on the left is in the S configuration, and the carbon on the right is in the R configuration. And that means that there's a mirror plane in this molecule that perfectly reflects one side to the other. And if your molecule has a mirror plane, it cannot be chiral. So below that, I have a couple of examples drawn out as dash wedge projections. Now, in the first one, you can kind of see the mirror plane, right? If you cut that molecule in half, the left half perfectly reflects the right half. And I've also added the configurations for the two chiral centers there. You can see that the one on the left is S, and the one on the right is R. And we know that S reflects to R, and they have the same parts. So they do, in fact, mirror one another. There's a mirror plane there. That is a meso compound. If you look at that second drawing, is that a meso compound? Well, at first glance, you might think, no, it doesn't look like it has a mirror plane. It does have the same components, the same groups attached to each carbon, so it could be a meso compound, but how could we tell? Well, really the only way to tell is to either build a model or determine the actual configurations of both those carbons. Now I've done that here, and you can see that it's the same molecule that I had drawn before. The configuration of the left carbon is S, and the configuration of the right carbon is R. There's always going to be multiple ways of drawing any chiral center correctly. In this case, simply rotating that carbon-carbon bond, keeping the left half stationary, and rotating the right half, I can make this molecule on the right look exactly like the molecule on the left. In other words, these are just two conformations of the exact same meso compound. So don't let that fool you. Just because it doesn't look like it has a mirror plane doesn't mean it's not there. You might need to do some free rotation to set up the mirror plane.